and we are very happy now to introduce for our Nobel Plenary Lecture, second part, Professor Steven Chu. Professor Steven Chu is the William R. Keenan and Junior Professor of Physics and Molecular and Cellular Physiology at Stanford University. His research spans atomic and polymer physics, biophysics, biology, biomedicine, and batteries. And the reason why he's here in this Nobel Plenary Lecture, he shared the 1997 Nobel Prize in Physics for the laser cooling and trapping of atoms. We were very happy and very honored to have Professor Steven Chu with us. He will be talking about energy and climate change. Climate change in this year also a very important topic. Some might be aware, some of you might be aware, we will have COP21, the Conference of Parties in Paris here at the end of this year. So I would like to welcome Steven Chu to talk about energy and climate change, and as he told me over lunch, also some other issues. We were delighted to have you here. Please welcome Professor Steven Chu. Thank you. Thank you for being here.
All right. Thank you very much. So if you can put on the screen, not me, yes. For heaven's sake, show my slides, not me. I'm going to talk about energy and climate change, but of course, I'm a scientist, so I'm going to talk about other things as well. And so opening this with a sun, a rising sun over the globe, and how it reminds us how essential light is to everything we do. Inherently, we're visual beings, and most of our data input, lots of our data input comes from what we see with our eyes, so much so that words like vision and insight describe qualities well beyond just the sensory input. And let me remind you that 150 years ago, the electric and magnetic forces were unified by Maxwell. And in those equations that you see circled, came out of something quite surprising, namely that electricity and magnetism were not only part and parcel of the same thing, but it predicted, in no uncertain terms, what the speed of light would be, but it was what the speed of light would be on things you can measure in the laboratory having to do with electrical and magnetic properties. And so from that grew something very important, and so much so that Albert Einstein said this change in the conception of reality is the most profound and most fruitful that physics has experienced since the time of Newton. And he was indeed correct. Now, when Maxwell was developing these equations and he's discovering that electricity and magnetism could form waves, he was constructing what is the electromagnetic wave waving? What is it waving in, and what exactly is waving? And he, in fact, tried to construct something that was mechanical. But in the end, this mechanical construction, he got a little bit frustrated, and in the end, all that was left, like the Cheshire Cat, was his equations. And this is actually what we're left with. The search of the mechanical medium which was waving was just abandoned. Now, since Maxwell's time, it was discovered infrared radiation, X-ray radiation, gamma ray radiation, and that was soon realized, soon being the next 100 years, that this was part and parcel of the same electromagnetic spectrum. It's quite amazing, but that this was very, very different sorts of phenomena. And as you heard and will hear in this following talks, we also discovered that light is not only a wave, it also has a dual part. It comes in little bunches, a minimum size, a certain graininess. Now, we actually work with electromagnetic radiation over 24 orders of magnitude. The lowest frequencies are used to communicate with submerged submarines, very, very low frequency. And there's a deep theorem in information theory that says the amount of information you can send and receive depends on the frequency of the carrier, electromagnetic radiation. So 100 hertz is very, very slow, very simple, slow messages, but nevertheless, it can exceed the information rate of many political speeches. Now, if you compare, sorry, to those politicians, but the highest energy cosmic gamma rays that are being detected are incredibly high. They're almost 10 to the 26 hertz, as opposed to 50 or 100 hertz. And Maxwell's equation said, oh, they all go at the same speed. And Einstein took this as a hardcore, he said, this is Maxwell's prediction, but I'll reverse it. I'll say, no matter what, they go at the same speed. And most recently, with gamma ray telescopes, we're able to test whether this is true, and to, apart in 10 to the 11, various gamma rays of different energies appear to go at the same speed across the universe. Now, I'm going to talk about energy and climate change. I'm going to talk about how science and technology is helping shape what we do, and I'm going to talk about other things. Here's the global land and ocean temperature record from 1860 to 2014, and you'll, if you just look at this data, could come to the conclusion over this period of time from 1860, the temperature was rising around the world. Surprisingly, in Washington, D.C., the conclusion is not reached. They look at that record and say, oh, over the last 12 years, it's roughly flat. What is this climate change business? Anyway, remarkably, 14 of the 15 hottest temperatures on record since we started taking temperature measurements occurred in the 21st century. I want to point out that the 21st century only has 14 years. It is getting warmer. Not only is it getting warmer, weather patterns are changing. This is information taken by insurance companies, reinsurance companies, that are terrified of major losses like big hurricanes, earthquakes, floods, crop failures due to droughts. And Munich Re has been accumulating this data from 1980 to 2013 of those events that trigger insurance losses. Not because they are deeply concerned about changing climate, but they're deeply concerned about how much to charge in premiums. And what they're finding out over the last 33 years is that events are changing. There's more stuff that's causing insurance losses. The same data, earthquakes, no trend. So earthquakes, no trend. The rest of the stuff associated with weather has been increasing. This is more data, something that as a scientist I love. This is the instrumental record of sea levels relative to land around the world. Again, from 1870 to 2014, the red is data from tidal gauges. The little green thing is data from satellites. And you'll notice that the sea level is rising. But in addition to that, the rate of increase in sea level rise is accelerating about 3 times faster than it was in the turn into the 20th century. And the predictions of the future are that it will continue to rise, but continue to accelerate. Glaciers are melting. The previous way we measured glaciers is you go to a glacier and take a picture of it. So this is Muir Glacier, August 1941. August 2004, it's different. But there's a modern way to measure whether glaciers are changing, and this has, again, to do with satellites. These are 2 satellites that orbit the Earth, and we measure the distance between these 2 satellites, and when the local gravity below the satellites changes, it perturbs their orbit. When it perturbs their orbit and we measure the distance between these 2 satellites to a fraction of a width of a human hair, you can actually back out the change in acceleration due to gravity. This is an example of that. Here we see Greenland, where you see maroon and blue. Mass, the local acceleration due to gravity, is decreasing. Where you see red, it's increasing. Oops, you don't see red. There is no red. You see green, where it's essentially stable, but the mass is decreasing. And in these little spots, these 2 glaciers, they show blow-ups of the data. The little oscillations are summer, winter, summer, winter. And so the ice mass is decreasing over this 10-year period, but it's not only decreasing, it's accelerating. And this satellite data is now measuring glaciers all around the world, and Some glaciers are increasing, but the vast majority are decreasing. Again, as we get this data, we're seeing both satellite from sea level rise, from Earth glaciers, that things are changing. I'm actually thrilled to tell you, this is only for the 5 atomic physicists in the room, that that satellite technology is going to be replaced with something using laser-cooled atoms in a satellite. My first PhD student is part of this proposal, and he thinks that this way of measuring gravity in satellites in space can be made maybe 50 times better. Now, let me draw an analogy between climate change and cigarette smoking. This is a record of smoking in the United States from 1900 to 2005. And during this time, the black is the average per capita smoking in the United States. By 1960, the average adult male was smoking 220 packs a year, including the non-smokers. And during this time, the blue is lung cancer deaths due to young adults. And it unmistakably rose above the noise, and the tobacco industry said, no, this is just a correlation, it's not causation. You haven't proved it. In fact, you don't understand it because you can't predict who will get lung cancer, who cannot. Therefore, it just may be a coincidence. And by the 1960s, the medical community had said, this is not a question of does it cause lung cancer, the question is how bad is it? And meanwhile, they were going on to stroke and heart disease. We now know, due to a massive campaign to discourage young people from smoking, there's a 25-year delay from the onset of smoking to the time you die of lung cancer. We now know that if you smoke a half pack or more a day, there's a 25 times higher chance of lung cancer, death. It's a big deal. We don't know what the damage is from the carbon dioxide already sent up there. We do know that during this time, the time of which we're putting up carbon dioxide, the delay time is unknown. It could be 50 years, it could be 100 years, it could be longer. The reason is actually simple as to why it's longer. The bottom of the ocean is very, very cold. When I was trying to stop an oil leak in the Gulf of Mexico in 2010, the surface temperature in the Gulf was 86 degrees Fahrenheit. The bottom of the ocean, where the oil was leaking out, was 2 degrees above freezing. It stays that temperature all year round. It takes many, many decades for it to warm up. So we don't know what the damage is that we've already done, and we don't know how long the CO2 will remain in the atmosphere, cycling between the land and ocean. It's anywhere from a couple hundred years to a couple of thousand years. So the delay time is not known. So here's what we're doing as a society. We take a deep puff of a cigarette, mainly we use lots of fossil fuel, and say, this is not my problem. And I don't want to sacrifice even a half of 1% of the GDP. That's someone else's problem. It's my great-grandchildren, my grandchildren, and their great-grandchildren going into 1,000 years. And so as a society, this is what we're doing. We don't know. There are a lot of risks, but the risks are huge, and the choices are bad, as in what we're seeing in strange weather patterns, really bad, or really, really bad. Okay, science is trying to figure that one out. It's just like smoking. Is it 25 times greater? Is it 10 times greater? Is it 50 times greater? There are other issues having to do with fossil fuel and automobiles. They make small particulate matter, 2.5 microns or less. We're only beginning this last decade to realize this very small particulate matter is very deadly. And in fact, in a recent article in 2014, it was determined that for every 10 micrograms per cubic meter of this small particulate matter, there's a 36% higher chance of getting lung cancer. The US EPA thing is 12 micrograms per cubic meter. Okay, the World Health Organization is 50. But for every 10, you get a 36% chance higher of getting lung cancer. Now, this is a picture of Harbin, China. The US Embassy in Beijing measures the outdoor air pollution of this small particulate matter. And in the year 2013, the yearly average was 194 micrograms per cubic meter. If you do the math, it turns out you have a 27 times higher chance of getting lung cancer. Except you do this, so everybody's smoking in China, well, including the one-year-olds. They're also smoking cigarettes, so it doesn't help. But the yearly average air pollution of this small particulate matter in China is significantly higher than the smoke rooms in airports, where you see those glass rooms and it's really cloudy in there. This is the average outdoor state of affairs in China. And so one is expecting hundreds of thousands to millions of people dying prematurely every year, but the damage is not going to be known because there's going to be a 20 or 30-year delay. All right. So let me talk about energy. And this is a question. I'm a professor, so you have to raise your hand, true or false. Renewable energy will become the low-cost source of electricity within 1 decade. How many believe that's true? How many believe that's false? Okay, most believe it's false, and the majority are not voting. Let's look at some data. This is not data from companies trying to sell you wind turbines. This is data from people buying electricity. So wind turbines are getting taller, they're getting more efficient. The big offshore wind turbines, which are very expensive, by the way, are getting very big. This is a moderate-sized one these days. The diameter of the blades is 93 meters. Just to put it in perspective, the Wright brothers' first flight was only 37 meters long. So 3 Wright brothers flights, and you make it from one side of the wind turbine blade to the other. Now, in the United States, when you build a wind farm, before you invest that money, you have to have a signed contract that says there's somebody that's going to buy my wind at a certain price for the next 20, 25 years. And those contracts are now being sold for 3 cents a kilowatt hour, $30 a megawatt hour. Just to put it in perspective, a new gas turbine in the United States, where natural gas is 3 to 3.5 times less expensive than Europe, that would cost 5 cents a kilowatt hour. Okay? I'm missing a zero there. Okay? So wind with its current subsidy is now cheaper than natural gas, and within 3 or 4 years, they won't need a subsidy. It will be just plain cheaper. In the United States, where natural gas is so much lower than in Europe. Solar is also getting cheaper. This is what's called a learning curve. Every time you increase solar module deployment by an order of magnitude, the price goes down by a certain fraction. You increase another order of magnitude, it goes down by another fraction. And this is data from crystalline silicon and thin film cadmium telluride. There was an overinvestment, and some companies went bankrupt due to an overinvestment in solar factories. The industry has now worked its way out of that. Price is stabilized at that red dot. And by 5 years from today, most of the people manufacturing solar, we say we have to sell at a profit at 50 cents a watt for a solar module. What does that mean? If you take when we started in the 50s and go to where that red dot is, the price of solar modules has declined 40-fold. Imagine buying a car for $20,000. You can buy it for $500. It's going to go down to $250. But that's not all, because the module is now a small fraction of the cost of solar power. It's the installation, the land use, things like that. But so solar is getting very inexpensive, and it's going to continue to decline as we go forward. Again, power purchase agreements. This is the decline in companies that put up solar farms and sell electricity on a long-term contract to utility companies, typically 20 years, 25 years. In 2008, those contracts were selling for 20 cents a kilowatt hour. They're now being sold for 5 cents a kilowatt hour from 2008 to 2014 in the United States. So this is real money, real contracts. Forget about what people are saying it costs. This is what they're signing contracts on. So now, the technology is getting better. That blue curve at the top, where you see gains in efficiency, this is a new type of materials called perovskites. It went from 3% to 20% efficient. It's not going to be commercially viable because it's still a research. This is research laboratory data, but never have we seen an improvement so fast in the efficiency of solar cells. This type of material can piggyback on silicon, and now the hope is for moderately low cost, you can get solar cells that are not 22% efficient, but well over 30%. Again, that will make the price of solar go down even more. The world has great solar resources. Wherever you see brown, yellow, it's pretty good. Even green isn't bad. Germany is in the green part. And so the United States, most of the United States, and most of where the population is, has tremendous solar resources. The United States is only beginning to take advantage of this. This is the total electricity generated by solar in the United States, nothing until about 1989. It puttered along until just recently, maybe 2009, things started to change a little and it started to zoom up. So what happened? Well, I became Secretary of Energy. Now, now I have to say, you may say that correlation does not mean causation, but it's actually incorrect. In this case, I was in charge of a loan program. I had to personally sign off on all the loans. Many of the loans we made were for solar farms and wind farms. The financial community did not want to invest in these because there was going to be payback over 20 years, but I thought it was a safe bet because they were signed power purchase agreements with utility companies. And so we made many loans. A majority of the loans were loans like this. The financial community, I will say again, didn't have an appetite for those loans. They thought it was risky. And they actually wanted to turn over the loans in 1 or 2 years. For example, mortgages, like junk mortgages, you bind them up, you securitize them, and you resell them. And that's the way they were doing business. This gets a payback in 2 decades. And so during that loan program time, we actually showed that you could make money. Our loan program, including the losses, like Cylindra, but including these, is going to make the government about $5 billion net, even though we were only charging 1.5% interest. We did significantly better than Wall Street, 2009 to 2013, even though we were charging 1.5% interest, okay? And so nowadays, the financial community thinks that it is a bankable industry, and Warren Buffett is buying some of our solar farms. So in any case, all that good except one thing. It's only 0.25% of the electricity in the United States, but that will change. Germany has the most solar, even though it doesn't have that good sun, followed by Italy, but China and Japan and the United States. Now, the countries that have the best solar of this group are China and the United States. Let me take this graph and show you what China's goals are and what the United States will probably do. By 2020, if I take that graph, China expects to be here. They are very serious about climate change, and the United States expects to be here. This is installed capacity, but because the sun is so much better in these two countries, you can double that from Italy and Germany. So this is all good news. Now I'm going to pause here a little bit longer. The really good news about solar is that these solar panels are becoming very robust. They're becoming lightweight. They're considered now in the United States with 20-year warranties, and they simply are not breaking down. So what is happening in rural areas is you're putting up solar in villages that don't have electricity. And once you have a solar panel in a village that can be right-sized to feed an entire village with a small battery source, or you can directly charge your LEDs to replace the kerosene lanterns, or you can use that electricity for cell phones, or you can use that electricity for a community refrigerator that holds medicine, or to purify water. This is going to transform the developing countries because it leapfrogs past having a grid. Even in the United States, there are sections of the United States which will never be connected to the grid. Western Alaska is one such thing. There's no people between Western Alaska and Eastern Alaska. There won't be a grid. And so with solar and batteries, or with wind and batteries, you can have this. Now, batteries is a big deal. And so you need batteries that can last in hot weather without being in an air-conditioned space, can work in cold weather, batteries that require essentially no maintenance. How are we doing on those? Not bad. The driver of this is actually batteries for electric vehicles. Batteries for electric vehicles in 2008 were manufacturing costs were $1,000 per kilowatt hour. In 2012, the price dropped in half. We in the Department of Energy said, how low do they have to get before you get widely deployed automobiles? And we said as a target for 2022, if they drop by another threefold, $160 a kilowatt hour, you will get a battery on a car that can go 250 miles that costs $25,000, which you can charge with solar. And at that point, we thought that this would be truly widely deployable, and this is all prices without subsidy. And so how are we doing? Well, this blue line is the cost of the battery and the battery pack. It was an estimate made by Bloomberg New Energy Finance in 2010. The X's are the actual manufacturing costs. And when Tesla builds its gigafactory, its manufacturing costs will be down here. Its manufacturing costs will be very, very close to what our goal was in 2022, but they wanted to complete the factory by 2016. Now, actually, I took the battery cost that Elon Musk was talking about. He said they can make it at $100 kilowatt hour, and I went up by, I put it at 180, okay? Well, I put in the Elon Musk factor. Anyway, so in any case, I'm very gung-ho on this. I think this is very realistic. Now, a favorite quote of mine, the Stone Age came to an end, but not for lack of stones, and the oil age will come to an end, but not for lack of oil. Actually said by a former Saudi oil minister. That's not why he is the former Saudi minister. He was merely saying that we will continue to lose oil, but when another better thing comes along, we will use that, just as when metals came along, we stopped using stones. We don't look at all the stones in the ground and say, unused assets. Not every stone has to be made into an arrowhead, because we went to better things. But let me also tell you that if we don't find a better solution, especially for oil, which is the key to transportation currently, the oil and gas will be used. And so that's why it is so important to develop new technologies like batteries, like alternate fuels of transportation. We're going to be using oil for 50, 80 years or longer, but in the end, we have to wean ourselves from that. Let me go on to other topics. And, in the beginning, there was light. It was a big light. It's called the Big Bang. As already mentioned, the universe, as we believe it, how it happened, started expanding very, very rapidly. And then in a brief period of time, about 380,000 years after the initial Big Bang, the atoms got neutralized, the electrons came onto atoms, and light could simply pass through. They weren't looking at charged particles anymore. And at that point, the light decoupled from the evolution of the matter. So that light provided a snapshot of the conditions of the universe 380,000 years after it was born. But just in case you're wondering, the universe is 13.7 billion years old. So it's really in the early infancy of the universe. What did we see? We saw an afterglow of the Big Bang. It was a perfect spectrum of what's called the black body radiation, and now we know its temperature to 4 decimal places. Pretty boring, except one thing. It was the same everywhere you looked. You look in this part of the universe and that part of the universe, exactly the same. If you went down in sensitivity by a factor of 1,000, you began to see something. It turns out the Earth is drifting in this radiation. As it drifts towards, in this direction, the black body radiation looks a little hotter, and it drifts away from it in the other direction, it looks a little colder. But this is 1,000th of the uniformity. In fact, the theory of inflation was made because it shouldn't have been the same everywhere. It should have evolved differently. Like once you're separated from this part of the universe, from that part of the universe, it's sort of like the evolution of animals in Australia is different than the evolution of animals in the mainland of Asia. They get different. But it was exactly the same. You go another 2 orders of magnitude, and it looks even finer, grainier, different. We think we're beginning to understand this graininess. You can divide the graininess into mathematical ways of dividing, and all those wiggles and oscillations are fit to our understanding of the universe. Staggeringly impressive. We also think maybe, maybe not, that this graininess can be interpreted in that inflationary period of gravitational primordial radiation. This, we know, this noise that you see here is due to the fundamental quantum noise that's inherent in everything we know in quantum mechanics, but it's now been exploded up to the size of the universe. Let me talk about microscopy. The telescope and the microscope really transformed things, and Leeuwenhoek's microscope was really the transformational instrument. He was a nobleman, but he made exquisitely good microscopes because he learned how to make exquisitely good little round spheres of glass. And very recently, in fact, this year's Chemistry Nobel Prize, awarded to 3 physicists, as it should have been, if you have normal optical resolution, a point of light doesn't appear in an optical microscope like a point of light. It appears like a blur, maybe 300 nanometers wide. But if you ask a different question, where's the center of that dot of light? It depends on the dot of light, the microscope, the wavelength, but also how good a signal to noise you get. So if you can find the center of that dot of light and find the center of this and the center of that and the center of that, you can get much better resolution. This technique was co-invented independently by Eric Betzig, Harold Hess at Genelia Farms, Howard Hughes, and also Xiaowei Zhuang at Harvard, and there are actually a few others. There were like 3 or 4 people who co-invented this. There's another similar technique called stimulated emission depletion microscopy, Stefan Hell, and Eric Betzig and Stefan Hell shared part of this year's chemistry prize. This is an example, it happens to be work on my lab, but it's an example of how good it's getting. In a conventional microscope, you're looking at a submicron cell, happened to be a bacteria that causes cholera. When we look in this probe that we now use, this is what you see. The picture's better. In fact, you blow up that little square box and you see this, and we're staining proteins that are emitted by these cholera bacteria, forming a protective layer to protect itself against the reaction of a human host against this organism. And so you can now see these pictures. Stimulated emission depletion instead, related but different. If you excite a blob of atoms in that, for example, that blue laser beam over there, you normally see atoms that then de-excite. But if you come in with another pulse of light, and before the atoms can de-excite, you force them to de-excite everywhere, except in that little small dot. What you end up seeing, then you wait for the fluorescence to naturally come out, you see only a little small dot. And this, too, shared the Nobel Prize, and it improved resolution 4-fold or so from normal optical microscopy. But in order to come in with that orange light to make the molecules de-excite, it has to be at very, very high intensity. So right now I'm just going to skip that, but in my lab, we're developing new probes based on old materials, but now in a nanoparticle. These are called rare earths, and we're exploring the idea of whether these can be used instead and used in, as new probes. They're completely photostable. Unlike quantum dots, they don't bleach at all. They're at least, as we're synthesizing these, equally as bright as quantum dots, but they could be brighter. And indeed, these are some of we're collaborating, we're also making them ourselves in our lab, but also working with Paul Avasados' group to make little quantum dots, 10, 20 nanometers, 5 nanometers wide. It looks very encouraging. Instead of using hundreds of megawatts per square centimeter to de-excite, instead, we will need hundreds kilowatts per square centimeter. And so, and they are going to be much brighter. And I'm just going to also note that the wavelength in which these particles emit are particularly transparent to tissue. And so that is also very good. And so we're very excited because we think that these particles can be introduced through the blood, target cells, get into the cells, like cancer cells or stem cells, and then you flood light through the skin, and you can, within several millimeters, look inside and locate where these particles are to submicron precision without puncturing the skin. And so we think we're very excited that this is going to happen. One last thing I'm going to talk about, and this has to do with, this is not my work, but it's, again, some new work that's come out in the last few years. If you take a laser beam and you focus it, as shown in this upper picture, if you focus it, you can get a focal spot that looks actually quite broad. But suppose you can make something by some tricks, mathematical tricks. So when it goes through an object, you actually make a line of light, a little pencil-thin line of light that doesn't actually disperse and come out. And so this is the idea. I'm missing one slide because I made the talk ending at lunchtime, but never mind. The way it works is as follows. I'll just describe it. Using some good optical and mathematical tricks, you make a pencil beam of light, and then you excite along this direction, and then you look with an optical microscope over in this side. And this pencil beam of light actually remains a very, very small, thin pencil beam for this entire length. And then you can move that pencil over here, and you make another image, and you move it over here, and you move it over here. So as you move this pencil over here, this lens is tracking where you move it and getting an image. And in that way, you can actually get three-dimensional images where you're only putting light where you actually need it to be and not anywhere else. And this is called structured illumination. And this is an example of the kind of 3D imagery you can get. Unlike super resolution, where in super resolution we're getting near molecular resolution, this is optical resolution, but it's 3D optical resolution in live cells. The nanoprobes we're working on, we want to get molecular 3D resolution in live cells, but this is also an important part of what we're going to be using. As you know, when cells begin to divide, there are these molecular materials that go off and they form spindles, and the spindles grow out, and then on those spindles, they assemble the chromosomes, and as the cell's DNA divides and a duplicate set of chromosomes come, they're pulled to the poles of those spindles, and then the cell closes in and divides. And so the next cells have all the DNA on one side, all the DNA on another side. This is a movie of raw data, not completely raw, they're putting colors in, of these spindles as they're growing and tracking. And so now in 3 dimensions, you can get about 30% better than normal optical resolution, but the point is you now have it in 3 dimensions. With the new probes we're developing, we think we can get molecular resolution in 3D with these movies. So with that, I see that I've really blown it. I've finished 4 minutes early, but anyway, thank you.